So yesterday we finished up talking about the concept of what a combustion reaction is. And remember, I didn't lie to you, I just didn't tell you the whole truth. And that all combustion reactions do not always involve hydrocarbons, and they do not always produce carbon dioxide and water, okay? So we're going to extend our knowledge, we're going to expand it. And they told you that one of the most famous combustion reactions in the entire world is what? No. Cellular respiration. So again, the reason that it's a combustion reaction, but it's varying to a certain degree, is because of the controlled mechanism of it, right? So we use enzymes to be able to dissipate the energy and spread it out over time, because if you were just like the whoosh bottle, it would just boom, it'd all be gone in an instant, and you just lay there like a blob, okay? So that's kind of what's going on in that. Now, some special combustion reactions, and this is the expansion of your knowledge to kind of take the place of the deal with the hydrocarbons. So, hydrocarbons or alcohols. Now, do me a favor and do this. So it's going to be CXHYOH. Okay? CXHYOH. That's going to be what they consider your alcohol. Y'all come on in. No, you're good. Y'all come on in. Okay? It combines with all that stuff to have carbon dioxide and water, right? Okay, that's the normal one that you guys have been used to. The second thing is ammonia. We've already talked about that one, right? So if you have ammonia, what's the formula for that? NH. Ammonium is 4, right? So ammonia is the third, guys. Y'all come. If you want to go ahead and fill in the back, welcome to. Okay, all right. You're going to produce. Again, we said that combustion reactions produce an oxide, right? So when you see NO, is that the oxide of that element? Yeah, okay. So in water with excess oxygen. Now, again, for anything to burn, what you got to have? Oxygen. That makes sense, okay? To produce NO2 and water. Now, these two are the ones they're going to get you. Those are the ones you got to kind of pay attention to as far as specifics. So non-metallic hydrides. Non-metallic. So what are you going to leave? What part of the periodic table are you not going to talk about? The whole left side, right? Anything from the stair-step side to the other one. And then hydrides. What do you think a hydride is? A hydrogen. Okay, so a hydride is going to be your anion in that case, right? Okay, so combined with oxygen. Again, notice we have to have oxygen for anything to burn to form oxides in water. Now, non-metallic sulfides. Same concept, right? Except with it being a hydrogen, it's going to be with a sulfur. Key part, really important. Sulfides. What group are they in? 16, so what's this charge going to be? S2 negative. Does that make sense? Yes? Okay. All right, thank you guys. See y'all. See y'all this afternoon. So, the sheet I just gave you a minute ago, solubility rules. I'm telling you now, forever and always, they will be with you and a part of your dear heart. Okay? So, if you will actually, let me pull them up. Let me pause the video. Okay, so here's the sheet that you have. Here's the way this works. Let me let it clear, and I'll explain. Okay, go ahead. We'll talk about that in a minute. We'll talk about it. So here's the way this works. We started talking about this yesterday. I told you 2 rules for solubility that were very important you're always going to see. What was one of the rules that dealt with the cation? All group 1s. So if you will notice, as a matter of fact, it is the first thing on, whoa, that's not going to work, okay? It is right there. All group 1s, and there's a small typo. You see where it says NH4, what's missing from that? The positive sign. Throw that on there for me. So NH4 plus is on there. So we've got group 1, and we talked about this yesterday. There's only there are 2 positive cations, right? 2 positive polyatomics. Is this one of them? So what this means, and notice what it says up here at the top. It says it is mostly soluble. Now when you say soluble, we know that this does what? It dissolves, okay? Dissolves. Sorry, it's still in highlighter mode. Is there an exception to almost every rule? Almost. Now, some of these don't have exceptions. And if you notice, here are your rules of exceptions. And this entire part right here says that there are none. What's wrong? What's wrong? I guess that's what I'm doing. So if you will go back and you'll look, the 2 that we talked about yesterday, we said group 1s and we said nitrates. Okay? And notice what it says by their exceptions. What are the exceptions for those? There are none. There's one more that I need you to memorize today. We're going to add to that rule. What other things never will precipitate? These things right there. What's ClO3 negative? Chlorate, and what's ClO4 negative? Perchlorate. Does that make sense? So those are the only these are the only three things that will never, ever, ever precipitate. Ever. What is a precipitant? When the anion or the cation reacts with its partner. Now, so basically the opposite charge, and forms a solid. Now, when we say solid, do I mean turn into a rock and sink to the bottom? Remember, it's that really small particle you can pour through a coffee filter and it comes right through, right? So that's what's going to be going on right here. Matter of fact, I've made a stupid mistake. I told you there's only one more that does not have a exception. What's the other one? Very good, thank you. So if you will commit those four to memory, these are the biggest ones. Group 1, nitrates, chlorate and perchlorate, and acetate. Anytime you ever see them, they'll never form a solid, okay? So is it possible to have a solid form of those ions? Yes, but as soon as you put it with water, what happens? It dissolves, okay? You with me now? Yes, so I guess I should have said that. So when with H2O, I think that clears up a whole lot of misconception. Thank you for saying that out loud now that I actually think about it from that perspective. Now, then we get into these bottom three, and all of a sudden we see exceptions. Okay, so this is whenever Mason said heavy metal bad guys yesterday, y'all kind of looked at him with that weird puppy dog look. It's like, oh, what's going on? So when he said heavy metal bad guys, this is what he was referring to. Okay, there are three heavy metal bad guys. Who do you think they are? Fantastic. Now, this is a stupid question, but it is one I need to ask. Why are they called the heavy metal bad guys? Okay, and in what way, what do you mean by heavy? Atomic mass. So if you look, lead is number 82, which is 207. Mercury is number 80, which is like 206-ish. Can y'all see that? I can't tell from there. I don't know. Here it is. I got one right here. So Mercury is 200.59, and then what's the other one? No, silver is 107. Okay, so as far as molar masses, they are significantly heavy compared to a lot of the other things that we see. Okay, so the main one that you guys need to be familiar with, are the halogens. Okay, they are. Screw that. Okay, so yep, right here. So do me right here. So write the halogens right there, and something interesting should show up or kind of set an alarm off. It's a mild alarm, but it's an alarm. No, in that same row. Say it again. Fluorine's not there. That seems to be a common trend. Fluorine seems to always be left out, right? And let's think about why. Let's think about what's going on here. We've already talked about this perspective. When we were writing our strong acids, okay, so our strong acids, we had three halogenic strong acids. What were they? Very good. So the one that we left off magically was this thing. Now, my question to you, and again, this is a follow-up of everything we've talked about before. What does strong reference? 100%, and I'm just going to write I for ionization, which means that it would break into H plus and F minus. And we've already discussed the reason it does not 100% ionize is because what do we know about F? It's too small, and it's the most electronegative. So think about this. If we flip the script and we're talking about an ionic solid, give me any group 1 or group 2 metal. I heard lithium. Of course you go with francium. So lithium fluoride. Of course you go with francium. Think about this. This is an ionic crystal. What has changed? We still have fluorine. We still have a group 1. The electronegativity, it's too small. Okay? So the reason that fluorine is not soluble very often is because of what reason? It's electronegativity, okay? So it's normally going to stay intact. So if I drop that thing in there, this is a trick question, would that thing dissolve? Ooh, would it? Yes, it would. Very good. So that's why I threw that at you. Okay, so that's why I kind of wanted to ask you. So what happens if I make it zinc fluoride? Hang on. I'll come back to you. Okay? Jamil, let's go back and ask, where's the confusion coming in? It will dissolve into lithium ion and fluoride ion. Yes. And the reason why is, let me go back and show you this. The reason why it would is because, read, I know this is a lot of, like, it looks like a clown wrote all that. Okay? Read right here. Takes precedence. What is takes precedent? It overrides everything else. So even though fluoride doesn't necessarily have a rule, anytime it's with a group 1, will it always dissolve? Yes. Okay. Does that now make sense? And here's the thing. Notice we've got a connection right here. There's your fluorine. Okay. It will dissolve unless it's with whom? The heavy metal bad guys, and then what? All of group 2. So notice what we left out. We left out group 1 because we don't even know about group 1s. They're always soluble. Yes, that's how you know. Yes, that's how I knew lithium fluoride dissolved. Okay, go ahead. Yes. Yeah, okay, now when you say pour water into it, and this is a silly question, but I kind of want to make sure we're understanding on the same page. What would be the purpose of pouring the water in there? Okay, yeah, I see from that perspective. No, always follow the acid rule. I'm just going to say always follow the acid rule. I don't know in actuality or reality if you could. Just. No, ma'am. Now, be careful how you say that. BAF 2. And I didn't mean, and I said that before I really kind of thought about it. So my apologize. So because this right here, because barium, when it's with fluorine, this is an exception. So it becomes insoluble. So it will sink like a pebble to a degree. Okay? Cannot dissolve. So this is how you read it. So it is mostly soluble, which means it will dissolve unless it's with one of its exceptions. So if we have lead iodide, it will not. If you've got lead bromide, lead chloride, it will not dissolve. Same thing with the other 3. Okay, go ahead. It will dissolve unless it's with all of those. It's not 100% insoluble, no. But there are, you see how it has the most exceptions? That's what I was trying to get you to understand, is that it will, but it depends upon who it's with. Okay, Tristan? Yes. Again, radium is radioactive, so we don't ever talk about it. Okay, go ahead. There's nothing you can put it with that will make it stay a solid. Always dissolve, no matter what it's with. You can give me any cation, and it will still fall apart. Okay? There's nothing that can hold it together. So now let's look at the bottom. So now notice what it says. These are mostly what? Insoluble, which means they will stay, stay a solid. Except when they get with these things, and exceptions means what? It does dissolve. Okay? Yeah. All right, well, then go ahead and add this in. Yeah, I don't know why it's different. Go ahead and add that in right there. It will always dissolve. Again, because if you go back to the top, you see where it says takes precedent. It doesn't matter. Any group 1 will fall apart, no matter what it's with. The asterisk Because group 1 and ammonium go to all of them. Instead of me having to type it every single time, that's because, look right here. Note, all of the above are subject to group 1 and ammonia exceptions, hence the asterisks. Go ahead. Yes, sir. Yeah, there in your little box where it has the note, there is a typo. Throw that, and I don't know why both places the positive was left off. Possibly. Right here on y'all's. Yes, sir. No, it's just a different order. Yeah, it's the same thing, just different order. Like I said, I don't know why mine's different. That's kind of weird. I've never really paid attention to that. I don't even know though. Okay. All right. So again, I know that this is a lot and it's overwhelming and it's cumbersome, but they are very vital. We're fixing to work with them. Okay. So go ahead and do me a favor. At the very top of this, write quiz on Monday. Okay. We're quizzing on this on Monday. That means you've got Friday, Saturday, and Sunday, and even tonight if you want to spend about 10 minutes. So here's my suggestion. Learn one box at a time. Tonight, memorize the top box. Saturday, and I'm giving you Friday night off because there's a lot going on. Saturday when you wake up, I know you got homecoming, memorize the bottom box. Sunday, do the top box. Sunday morning, do the top box. Sunday night, do the bottom box. And then do all of it before you come in here on Monday to take the quiz. Do them one box at a time. Don't try to memorize both. Do them one box at a time. Go ahead. No, the whole thing. You don't have to do this, but here's how I want you to do it. Study like you're going to have to come in and rewrite that entire sheet. You rewrite it. And you're not going to have to do that, but that's the best way to prepare. Basically, it's going to be kind of like that, and there are going to be blanks that you've got to fill in the blanks. Like it's either going to be I'm going to give you if it's soluble or insoluble and its exceptions, and you got to know which one fits its exceptions. Or I give you the ion, and you got to know if it's soluble or insoluble. Or I'll give you the ion, and you got to know its exceptions, if it has any. No, you have to write the whole thing. No. It looks similar, but it's not the same. No, you don't have to have the patterns. That's just for you mentally to help. Yeah, just the boxes. Just what's in the boxes. All right, so let's go back and let's actually work with some of these with your sheets. So like I said, here, I don't know why I didn't just pull this up. I forgot this was here. All right, so again, these things are mostly soluble, which means, go ahead. I apologize. Yes, ma'am. It would, because it's not an exception. So that example that I gave you a minute ago was zinc. I was wrong. Because zinc will dissolve. Yes. My apologies. Yes, ma'am. Absolutely. And the reason I'm never going to not let you use the periodic table because that's unfair to you. Like you get it on every test. No matter what we do, the periodic table is your cheat sheet. If you can use it to your advantage, do what? Green one. No, always the green ones. The reason why you're always going to get the green ones is because that's what you're going to see on the day of the AP exam, and I don't want you used to those old ones that actually tell you more than it should. Okay? It tells you the name. It tells you a lot of stuff. Those old yellow ones. Yes, sir. Tristan? That's actually a good question. Y'all need to hear this. What he just asked is, for right here for heavy metal bad guys, it says PB2+, silver 1, and HG2 2+. It's just for lead 2, not for lead 4. Okay? Second, Tristan? Yeah, scratch out the 2. That's another typo. Thank you for catching that. Silver's always a what? Always a 1. Which one is that on? Oh, wow, it is on all of. Well, y'all, my sheet is correct, and I need to just throw all those extras away and print the new ones out and give them back out. Okay, my apologies. All right, so again, this is the same thing. This is in your notes if you want to see it again. Now, this is another way to read it. I want to give you, sometimes you guys like boxes, sometimes you got like charts, sometimes you like words. I'm trying to hit all of your learning styles. Yes, ma'am. There's even a song, if you look up on YouTube, a solubility song. I'm not going to play that for you. Okay, go ahead. No, I'm not. Oh, Stephen LaFleur. Yeah. So, disclaimer. It's way more fun if you name them. You are probably more creative than I am, but don't refer to the solubility rules in this way when answering free response questions. Again, if this is something that helps, I'm willing to give you guys any resources that will be an aid to you. And if you memorize it this way, that's fine. Kind of like when we did polyatomics. You know, somebody ate a clam supper in Phoenix. Nick the camel ate it. All right. So that's kind of something here. So Big Mama. I don't know again why it's called Big Mama, but it says all nitrates are soluble. Yeah, all good cats put dirt over their pee. Okay. Now the next one, Big Daddy. Okay. All group 1 metals and ammonium are salts are soluble. I don't know. I'm just. This is probably going to come out very insensitive or sexist, and I don't mean it that way. But mama nitrates are negative. Male or metals, ammonium are positive for males. Again, I don't mean that in any negative connotation, but I'm just throwing that out there. Okay? I apologize. It is bad. It is really bad. Again, I didn't come up with this. Is not mine. All right. Stay with me real quick. So again, the halides, chloride, bromide, and iodide are all soluble except with, again, the heavy metal bad guys, silver, mercury, and lead. Strong acids, hydrochloric, hydrobromic, hydriodic, nitric, perchloric, sulfuric. Write these dissociated. I do want you to put a big star beside number 4. Where it says bold and underline. Write these dissociated. Underneath that, please write in ion form. Okay? In ion form. So what that means is when you write these ions, and we're going to get to this tomorrow, is that when you see these things, you must write them how they're in their ionic form. Okay? So instead of writing HCl, you would write H plus Cl minus. We'll talk about that tomorrow. You're going to see that. Number 5, same thing, strong bases. Hydroxides and oxides of group 1 and CBS of group 2 or Cabasur, however you want to memorize it. Is there a reason y'all are holding pinkies? Because that's really weird. Please. Then move. Then stop holding pinkies. That's really awkward. Like, for real. Like, you're making me uncomfortable. Yes, ma'am. Yes. BOH minus. Okay? All right, so here's an example. Write the chemical equation for the aqueous reaction between barium nitrate and sodium sulfate. We did 2 examples just like this yesterday. I want you to write both reactants, predict your products, and try to state their state of matter for all 4 of them. Okay? Now, I'm going to do it in this, and I'm going to come back and show you the long way. So here are the ions that should have been present. You should have had, write it in the color you can see it in. You should have had the barium ion. You should have had the nitrate ion. You should have had the sodium ion, and then the sulfate ion. So those are your 4 possible ions. Okay? So your possible products. I don't even really know what that's wanting you to do. So I kind of see it, but I'm going to write it the best way to do it. All right, so we know that we've got barium nitrate, so BaNO3 2 plus Na2SO4. And so double replacement, I've got BaSO4 plus NaNO3. Now, up here, it says write the chemical equation for the aqueous reaction. When you see that, what does that tell you? They are aqueous. Now, let's talk about how we would know based on solubility. Barium nitrate. Very good. The nitrate makes it soluble. Okay, so that's aqueous. What about sodium sulfate? Okay, group 1. Okay, let's do the easy one. What over there on the far side is definitely aqueous? Okay, we do this whole thing because it's a group 1 and a nitrate. So now we've got the other one we need to actually think about. This is where your memorization of the solubility rules must come into play. So what I'm going to do is I'm just going to kind of back out of this real quick, and I want to look at, if my mouse will play nice with me, okay, I need to look at that's the wrong button, my solubility rules for sulfate. So here it is. Sulfate is mostly what? Which means it will dissolve unless it is with whom? Heavy metal bad guys and Ka-Ba-Sur, or CBS of group 2. Is that cation specific to our sulfate? Yes. So what does that tell you about barium sulfate? What will it be? It is insoluble, which means it is an S. Very good. Yes. Okay, so we've got barium 2 plus and barium 2 minus. Sulfate 2 minus. My bad. Very good. Thank you. Okay. And that's what I was fixing to say. It's got to be the sodium nitrate. Okay. Now, I'm just going to throw this at you. I don't want you to do it, but I want to talk about it verbally. What if they told you that you had, let me write it in white, that you had 500 milliliters of a 0.250 molar solution in excess sodium sulfate, and my question was, how many grams of that could you get? That is a legit style problem that you very well could see. That I want to know how many grams of my solid precipitate were formed out of that. Very good. So we need to do this to get our number of what? Moles. Now, here's my first question. Can you take the numbers as is and use them? What do I got to change? Very good. So 0.5 liters. Okay, so what's 0.5? I could have done it a little easier. What's 0.5 times 0.25? I really don't know what that is. I'm just asking Dustin. 0.5 times 0.25. Is it? Sounds good. Okay. So some of these kids are math wizards. Just whatever. Yeah. I'm not kidding. Now, the good thing about this question is what? Very good. As soon as you see excess, you should be kind of doing that kick for joy, right? Why is that good? Very good. We don't have to find limiting reactant. Then it's very simple from here. You go from moles of this to grams of that. Okay. You gotta find mass. It's a pain in your booty. Okay. Go ahead, Jamila. What's wrong? What's wrong? Say it now. Okay. All right, so here's what I want you to do. These three, these are your two reactants. So you don't really have to do the full reaction. I want you to write both products and predict all four, actually, of your two products. Predict their states of matter for the two products for each one. Does that make sense what you're doing? Okay, so part A, write what the two products would be, and then state if it's aqueous or solid. They're all double replacement, yes. Yeah, the and is a plus, and then you would just write it underneath it what the two products would be. Okay? And then use your solubility rules to determine if it's going to be a solid or if it's going to be aqueous. All right, Chance, help me out. What's one of my reactants in A? Just give me one of them. Okay, so potassium, so what is it? K what? All right, and what would your state of matter there be? Very good. How do you know it's aqueous? Very good, okay? All right, Edward, what is my other reactant? No, come on, Edward. Okay, BA what? Very good, okay? All right, so Edward, what state of matter would it be in? Very good, and how do you know it's aqueous? Very good, fantastic, okay? Mary Beth, what's one of your products in B? Okay, very good, and what's the state of matter? How do you know? Very good, both of them, it's got both whammies, okay? All right, Nicole, what's your other product in B? Okay? Now, I'm going to say this out loud because I think it's important. Nicole, this is, I just want to make sure. Why do you not have any subscripts in that one? Very good. So what we assume, and we've talked about this, lead as a 2 is a reactant. Is it possible for it to change? But what are we going to assume? That it does not, okay? Unless otherwise stated, assume that it stays the same charge, okay? Now, Nicole, what is going to be this state of matter? Very good. And how do you know based on your rules? Very good. So it's insoluble unless it's with one of the heavy metal bad guys, and it's led to one of those guys. Yes. Are we good on that? Yes. Okay. All right, Ryan Howard, give me one of your reactants or one of your products in C. Okay. And what's its state of matter, and how do you know? Okay, so you got both of them. All right. Jamila, what about the other one? Which iron? Okay, so give me the formula. Okay. What is the state of matter? Very good, it's a solid. And how do you know it is a solid? Okay, what's the rule for hydroxides? Yep. Very good. Group 1 or Cabasser? Yes, very good. Okay, it's group 1, ammonium or Cabasser. And I'm going to be honest, I don't talk about ammonium a whole lot. It's just not a part of how I say it most of the time. Okay, all right, so describing reactions in a solution. And this is where things are going to kind of start turning for depth. What's wrong? Okay, this is where, again, I didn't lie to you. I just didn't extend the full truth to you yet. And this is where things are going to kind of start changing for us drastically. So we have 3 different ways we can write a chemical reaction. We have a complete balanced equation. We have a complete ionic equation. And then we have number 3, a net ionic equation. You guys have always done number 1. That's how you've always done it. We're going to have to learn how to get to number 3. And the number 2 is the step in between. I'm only going to do step number 2 very few times because you're going to find out it is long, it is laborious, and it is aggravating. And so you're going to want to learn how to go straight from 1 right into 3 very quickly. Okay, Justin, go ahead. No, we're not. I promise you haven't seen it yet. We did it, but very small dose of it. Okay. All right, so number 1 gives the overall reaction stoichiometry, but not the forms of the reactants and products as they exist in solution, the way we taught you again in first year chemistry. Number 2, this is the complete ionic equation. It represented as ions from, and do this for me, circle or underline, all reactants and products. Somebody let him in. All reactants and products. That's number 2. It's ions from all reactants and products. And I'm telling you now, it's going to get long, it's going to get laborious, it's going to get aggravating. It's your fault. You left them. I didn't eat them. I don't eat hot Cheeto and lime. That's gross. Okay? Question. Somebody had a question. Ask someone. Yep, that's exactly what we just did. Okay? Now, number 3. The net ionic equation includes only those solution components, and circle or highlight this, undergoing change. So what we're going to do is we're only going to focus on the things that are actually doing something. Everything else that is there just to hang out and chill and watch, we're going to get rid of. Now, we have a name for those things that are literally doing nothing in the reaction. They're just hanging out and watching. What do we call them? Spectator ions. So when you go to any sporting event or an opera or a concert or whatever, you are a spectator at that event. You are not participating in the actual event that's going on. Okay? So we need to get rid of those things and eliminate them because it clutters up our equations. Okay? It makes them more difficult to understand. We want to focus on the chemistry, not the stuff that's causing us problems with the reaction. Okay? So spectator ions are not involved in the reaction process. It's started and finished as an ion. Highlight that sentence for me right there. Okay? It started and finished as an ion. So here's the mental thing or the visual thing that's going to help. You're going to be looking for 2 things. You're going to be looking for a change in a state of matter, which is always easy, or you're going to be looking for a change in oxidation state, and that's the challenging one, and we'll get into redox next week. So again, you must always look for things that are changing, and if it stays the same, what do we do with it? We get rid of it. Okay, we don't pay any attention to it. Okay, there's always a conservation of charge in net ionic equations as well, and we'll talk about that when we get to redox. Okay, so net ionic equations are the most important formulas from here on out in AP Chemistry. You have to know how to do these, and the only way you can do these is practice, 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 and you must also know what? Your solubility rules. Okay, so this is what I call the BBC method. Okay, y'all know what the BBC is on TV? What is it? There you go, the British Broadcasting Company, but we're going to call it the balance, bust, and cancel method. Okay. So, and it kind of sounds silly, but again, I think you guys have learned over the past 2 years that I'm very methodical in my approach, and I do things the same way every single time. And if you will follow the BBC, it will always work the exact same way every single time. So, what we're going to do is we're going to first write the balanced overall molecular equation. So we're going to do what you've always done. Okay, that's the balance part of it. But then we must bust anything that is soluble. So out to the side of this, how would you know if it is soluble or it has what state of matter? So out to the left of this, please write look for AQ. So step number 3, look for AQ. Okay, so if it's aqueous, we're going to bust it up. And what are we going to bust it into? It's ions. Very good. So if you want to write that somewhere around that, we're going to bust it into ions. Only the soluble things. If it's a gas, it's a gas. If it's a liquid, it's a liquid. If it's a solid, it's a solid. You can't bust those things. You got to leave them alone. Leave them as they are. Okay? And then finally, we cancel the spectators. And how can you recognize a spectator in an event? It stays the same, it doesn't do anything. Okay? Yes, sir. Okay? So we're going to look for things that are identical on both sides, and we're going to get rid of them. Can you let her in, please? Okay? All right, so here's our first example. Yes, ma'am. All right, Esteban, read me this sentence by name. Read it to me in words. Shh. Lead what? Okay? Okay, what does it do? Okay, and what does it do? Read the whole thing to me. Yeah, like if it were in paragraph form, how would you read that entire reaction? Reacts. Two potassium iodides, which yields, makes, produces, creates lead what? Lead 2 iodide, and it's what we call that? Not a solid, it's a P word. It's a precipitate, okay? So we have a solid lead 2 iodide precipitate, okay? And no. Okay? Very good. Does that make sense? Okay? So this is our complete balanced equation like you guys are used to seeing. Well, here's what we've got to do. We've balanced it. Now we got to do what with it? We've got to bust it. What are the things we got to bust? Okay, so everything that's aqueous, write the word bust above it. Okay? Bust. So everything that's aqueous, we're going to bust it up. So we're going to bust this, we're going to bust this, and we're going to bust this. Those 3 things. So lead 2 nitrate, potassium iodide, and potassium nitrate. We're going to bust them up. Why can't we bust lead 2 iodide? It's a solid. Leave it alone. Now, what are we going to bust them into? Ions. Very good. Is all this filled in? Okay, that's fine. So you can kind of see where we're going with this. Now do you see what I mean by the complete ionic equation is laborious and aggravating? Do you see what happened there? It looks awful. I don't want you to do this, but I'm showing it to you so you can mentally and conceptually understand how we get from the complete to the net. Now I want you to think about the word net outside of science. Like if I want to know your net bank account, what does that mean? Okay, so do you agree at the very beginning of the month you start with a certain dollar? Okay, what is the net result? It's everything that you have spent and deposited throughout the month at the very end, right? That's your net result. Hopefully, it's more than it is at the beginning of the month. That's what you're trying to figure out. So your net result is everything that has changed in between. So what we're looking for is after we balance and we bust, what do? We cancel, okay? So how do we know if we can cancel it? It's visual, if they're identical. So the one thing that we need to do is we need to circle the things that we didn't bust up. So go ahead and circle that lead 2 iodine. So here's where the busting comes into play. So let's look and see. Lead 2 plus. Does it look the exact same on the other side? Nope, so leave it alone. NO3 minus. Does it look the same? Yep, so what are we going to do? We're going to cancel it. Hang on 1 second. Go ahead. No, just the ion itself. Ignore the coefficients. Okay. All right. K plus. Does it look the same on both sides? What do? Eliminate it. Okay. I minus. Does it look the same on both sides? Nope. So now do you see what the cancel method looks like? So if it looks the same, what do we call those things? Spectators. Okay. So then what the resulting thing is what you're left with after you cancel, which is our net ionic, which should look just like that. Does that make sense? So visually, it's a lot, but I think you understand the concept behind it. Go ahead, Justin. Huh? That's an ion. Trevor. Here's the way I always say it. After you bust everything up and cancel it, in the very end, go back and double check and make sure it's balanced properly. So if you look at that red formula, you've got 1 lead, 2 iodines, 2 iodines. Now, do me a favor. I do want to go back and show you this. So stay where you are. Just read this last sentence right here. Actually, right here. The very bottom of this, notice what it says. There's always a conservation of what? Charge. So let's go back down and look at this right here. So we must make sure that both sides have the same charge value. So let's look at the product side first. What is the charge of PbI2? It is neutral. There's nothing. All right, well, over here, we've got 2 positive plus what? 2 negative. So what's the overall charge? So does the charge hold itself as well? Okay, go ahead. Yes, you're looking at the ion itself, not the coefficients. Don't worry about the coefficients. Okay, go ahead. Very good. Yes. It is not I2 right here because it is an ion form, not elemental form. If it were I2, it would have to be a solid back there. How do I know it's a solid? What color is it up on that back one back there? Chance. Will you go open that door back there? The end of the hall. Hey, somebody's coming. Thank you. Okay. Nothing. No. All right, so here's what I want you guys to do. Let's actually do the first one together, and then I'm going to let you do the second one by yourself. So it says an aqueous. All right, so for each of the following reactions, right, the molecular, the complete ionic, and the non-ionic equation. So we're actually going to do all 3 of these for the first one. And I know it's going to be long, it's going to be aggravating, but I'm only going to do this a few times. So an aqueous potassium chloride. So how would I write that? KCl, and what behind it? AQ. Okay, it's added to aqueous silver nitrate. So I've got Ag what? Why are there no subscripts? Silver is always a what? 1 plus. Okay, to form a silver chloride precipitate. What would be your formula for silver chloride? Very good. And what state of matter? Solid. How do you know it's solid? It says the word precipitate. Plus aqueous potassium nitrate. Potassium nitrate is K what? NO3, and it is aqueous. This is the part where you're going to want to start throwing stuff at me. First of all, why is this really easy to balance? What are all the charges and all the ions? They're all ones, okay? So again, this is the part where you're going to hate me, but I need you to see it so you appreciate the net ionic. So we've balanced. Let's bust it. What are we busting? That's a what? Except the solid. So I've got K plus Cl minus plus Ag plus NO3 minus yields solid AgCl plus K plus NO3 minus. Yeah, I get it. It's aggravating, but I think it makes you appreciate where net ionic comes from if you see all of that garbage. You got that, Nicole? Fantastic. Just making sure. Say that again. No. Once you bust it, the ion should tell you what state it's in. You don't have to put AQ behind everything. Yes, sir. For me? Okay. Gotcha. Thank you. All right. So we've balanced. Go ahead, Nicole. Okay. We've busted, and now what do we do? Cancel. How do we know if we can cancel it? If it's the same. So K plus, is it K plus over there? Yep. All right. So let's get rid of it. All right. Cl minus, is it Cl minus over there? So leave it alone. Ag plus, is it still Ag plus? No. Leave it alone. NO3 minus? Yes. So let's get rid of it. Okay. So what we then do is we write what's left over. Okay. So I've got Cl minus plus Ag plus makes AgCl solid. Hang on. Very good. That is solubility rules. You're seeing it now kind of come to light. There's one last thing I want to ask you. All we've ever done is balanced atoms. I need to add one more thing to your repertoire. Not atoms. What else do we need to make sure is balanced? Charge. What is the charge on the product side? Neutral. On the reactants, we've got one minus and one positive. Neutral. So does it balance? Fantastic. Mary Beth, go ahead. Yes, ma'am. If it's in its ion state, that automatically tells you it's aqueous. Okay. Now, and I want to say this out loud. What was I going to say? Okay. What the students struggle with the most is how in the world or why does all of this other stuff matter, and where did all the potassium and the nitrate go? If I hold that beaker up in front of your face, do you agree that solid chloride is going to be floating around as little solid particles? Is the potassium and nitrate still in there? But why don't we show it? Did it have anything to do with the reaction? No, it's hanging out cheering and watching them go. Okay, go, 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 go. Right? That's all it's doing. So you don't have to show that it's present. All right, you guys see if you can do B, and I think we're going to run out of time by the time you finish B. Okay. Awesome. Perfect. Stuff? What do you mean stuff? Yeah, we got to do that today. No, we got to do that today. Yeah, coefficients don't, until the very end. There is. It's